here's a fun one. So Intel wanted to have, when they rolled out the x86 architecture, this is what they wanted to have happen as far as the way that the developers broke out their applications. But in reality, what got implemented was this view on the left-hand side. So you can see where they've made the conscious choice of going like, okay, we should really break drivers out away from the kernel just from a stability standpoint, security standpoint, et cetera. And the developers are like, well, that's great, but we're just going to do this. We're going to put the OS and the drivers right in the same ring, which has some security implications, of course. But they did that for backwards compatibility issues, and just I'm sure if I talked to somebody that was back doing this in the day, they'd have some better reasons about why to do that. But
actually, I looked into that a little bit. One of the reasons they decided to implement it that way was essentially whenever you want to pass one of those trust boundaries, that costs you some amount of a performance hit. So they just wanted to remove anything that wasn't a direct user space kernel transition, and everything else just kind of gets lost.
And of course, the little artifact here is IBM OS2 decided to do all of this. So if you guys want to run a system with isolation, that would be the one to choose from right now.
No wonder it was so stable.
Yeah. So here we got the hypervisor rings. The thing to take away from here is we have, right here we have the privileged ring 0, and then we have a deprivileged ring 0. So this is our guest, and this is our host. But what they've done is they've gone ahead and given the guest ring 0. However, that's actually is missing the access to CR 0 through 3.
Yeah.
And so that actually is not exactly a true ring 0 on the guest, which gives you some more process isolation.
And this would again be a difference that differentiates what particular virtualization technology you're using. So if you're using an AMD V versus an Intel VT, they actually implement how the GDT, LDT, IDTs are handled. Under AMD, they actually use the nested page model, which is actually really efficient. Under the Intel model, they actually allow sort of a number of models, but they don't support a nested page. But each of those presents a different sort of potential attack profile, and we started seeing that with cache timing attacks to be able to either have pages mismapped into another page of the virtual machine or to just detect that another system is active.
So you can start to get an idea here that your attack surface is growing. It's very much at the silicon layer. And so it's going to be very useful to pick up some of the x86 programming guides and get familiar with this technology sooner rather than later.
This slide is actually one of my favorites here. Now, like I just recently tried to figure out and decipher what this slide actually meant. And then, diving into the documentation a bit more, you can actually see down the bottom they have this node DMA where the display adapter goes through. That's, I believe this is from an Intel document. Yep. So that's actually Intel recognizing that DMA is a problem. So, for example, a FireWire attack under this system, if your host-based system actually supported FireWire, that would be a potential threat to your hypervisors on a physical level. But that also means that things like network cards and other devices are. The problem here is that the no DMA is actually implemented on the MCH, which itself has the ability to talk to the host system and, again, becomes another target for vulnerabilities. We're also seeing places where network cards like, I'm sorry, not network cards, but other external devices like the NVIDIA card is one that I use. You can map pages of memory back and forth between the device and actually define where it maps that back. And if there isn't something very good at protecting it, you can stomp all over some things.
So growth over generalization is basically a hardware-based firewall for the mapping and unmapping of memory pages. So it's a after-the-fact introduction.
And you can also see that sort of the primary method of handling virtualization here is through the VMM. It's actually, this is again through the memory controller hub. As a memory request comes in from the CPU, it hits the memory controller hub, which decides who actually owns that piece of memory, and that actually returns control to the VMM.
And the thing is, with virtual machines, everything's done through memory. So if you have 100 virtual machines on one host, just keep in mind that your network paths are actually their bits being flipped around in physical system memory. It's never hitting the wire. It can be accessed. If you can get access to the paging system and know where memory is being allocated, then you own the system. Here's a Legrand, which is now called TXT or text. This is their secure boot process. This is the idea to try to circumvent some of the blue pill level attacks by trying to enter into a known, trusted compute state. There's been a lot of thought put into this guy, and you can see it's pretty complicated. But the Invisible Things Labs folks went ahead and they pretty much, I don't know if they've taken most of their life force, it seems like, and they've systematically broken each Intel security mediation on the hardware front to show that little sender doesn't always get called, and they can shim in there before sender gets called. And it seems like this cat and mouse game with those guys, but they do a pretty good job at it.
Yeah. So this is, I think this is actually under currently Intel's TXT technology. Intel actually has a number of different virtualization pieces that go with it, and this is the TXT, and only available on select motherboards and chipsets.
Yeah, so when you're making your choice, you're like, okay, I'm going to build my secure cloud, you need to really dig in, because just because it says, it might not actually implement the entire hardware protection set that you could get from Intel. You have to marry the chipset with the actual processor that you're using. Yeah, and that. You know, we need to get into that. That'll be the next version 2 of this, and we'll provide it. Yeah, I apologize for the AMD folks, but AMD has similar technologies. They actually came out with the secure virtual machine idea before Intel did. Okay, here's a hypervisor attack surface. It has a lot of attack surface, and so we're going to just briefly go over what that is from an attacker's perspective, because if you understand how the attacker thinks, then you can understand how to go about defending it. Here's a quick attack surface analysis. It's not overly accurate, but it kind of gives you the idea of where things sit. So ring 3 is where your guest operating system sits. Ring 0, your privileged state, is where your hypervisor sits. And unfortunately, to a lesser extent, some of your management system. So you've got the remote to host. Everybody understands that. It's somebody on the internet attacking the actual guest system itself. So you're running an unpatched version of fill-in-the-blank web server. You're able to get a foothold onto the guest operating system. From there, you might be able to leverage down into the host operating system. Remote to guest, that would be remote to guest. Remote to host would be actually attacking. Sometimes these hypervisors come out and they're actually exposing DOM 0 or the server core or the ESX admin interface to the internet or to a local LAN segment. Never ever do that. These things, if you dig around in the CVE articles, they have nothing but massive unpatched attack surface. I mean, things like copying malicious fonts into X11 directories, taking out your hypervisor. I mean, it's no end to it. I actually lost count. There's so many vulns out there right now for the actual management piece of the hypervisor. So I think maybe one-way diodes talking to that, almost treat them like SCADA systems in a way. Like make sure you have a solid air gap between the management interface, the allocation, deallocation of virtual images. It's a big deal. And then you've got a guest to host. You have a massive attack surface there. You have the guest can attack the tools interface, the VMI interface, the hypercall, hypercall, VMI, they're all kind of in the same bucket. So this is actually the guest operating system calling into the hypervisor through exposed APIs. And if you want to talk about the I/O backdoor, is that good?
We went through that. I think we covered that a little bit at this point, but that's mostly just the sort of secondary kernel interface that you would actually be passing these calls through on a lot of these.
There's a fun attack where people are trying to figure out how to patch the BIOS, and then from patching the BIOS, they create a malformed E820 memory map that gets fed back into the hypervisor and then owns your hypervisor. It's kind of a chicken and egg game, though. Like, if you've got that level of access, then why own the hypervisor? But it's like, really? So you can, from the bottom up, you can own the hypervisor, and from the guest down, you can own the hypervisor. Hypervisor, for the management interfaces, exposes a networking stack that can be compromised. So there's all these interesting angles that you have to keep in mind when you're going to deploy your private cloud.
And then there's some weirder things that also end up showing up, especially when you're talking more public cloud, I suppose, than private cloud. But the virtual system images themselves start becoming potentially hostile images, and CD-ROMs I've sort of already covered. One really interesting anecdote somebody had given me is actually suspending a system under an AMD device and restarting the system under an Intel device, and that actually crashed the hypervisor. And one of the reasons that some of this stuff seems to happen is that under some systems, and I'm just taking the shortcut out of this, right? So they may have SSE2, SSE3, and then they move to a new system that doesn't support these, and suddenly the VM thinks that these invalid instructions are on their way to being executed anyway, and that generally brings the system to a halt. And we keep seeing these other surfaces now that get exposed, like the web interface. Amazon's EC2 is a really interesting one. If you've got your whole corporation sort of integrated into that, like one good cross-site scripting bug.
And Amazon has a two-factor token, as probably sure everybody's seen, so I definitely highly recommend grabbing that guy. You can buy it right off the website. So those are some things to keep in mind. People are, there's like an integer underflow in the E1000 driver that you probably like, if you think about that when you're like, so there's an integer underflow in a networking driver. Oh, that networking driver gets virtualized. So now you've got your guest operating system that you've spun up on somebody's massive cloud infrastructure, and you literally have a virtual interface that has a buffer overflow or underflow or whatnot that you can attack to get into the hypervisor. So we're talking like if you want to look at the number of inputs into the hypervisor, it starts to like boggle the mind, or at least mine.
Actually, since you covered the E1000, another sort of side effect of the E1000, you can look this one up. It's actually a really fun vulnerability. You can actually feed the E1000 various MTU sizes and get the E1000 to sort of say, that's not a valid message, I have to fix it. But it only fixes it enough to pass it to the host system, and then it just sort of gives up on it. Some really clever people have figured out that essentially they can send it a sort of large MTU packet with a normal packet that would normally be rejected by the system's firewall in the first part. But the way that it actually reformats the packet is by splitting it and allowing a new header to actually be formed, and that becomes a new packet that has already passed the check. It is now already inside the network, and at least one way you can potentially talk to other hosts. It wouldn't be a bidirectional communications thing, but that was a really clever issue with the network card.
Complexity is definitely the enemy of security. This is probably way too small to look at, but we'll go over a couple of these bugs.
I can't read it.
So in 2006, it's kind of when we first started seeing some attacks against hypervisors, virtualized rootkits. In 2007, we saw the Xbox hypervisor exploit come out, which was a big deal. They had to like do some serious engineering on that to fix that bug, basically risking the games from being pirated and whatnot because the hypervisor got exploited. Virtual PC had a buffer overflow on it, a heap overflow in the VMware VM system. And so we kind of see this. This is just 0.005% of the known vulnerabilities right now against hypervisors. So don't think when people are like, well, I've never really seen a valid attack against a hypervisor, you have to read closer. Yeah. Because what they're saying is they really don't say like the hypervisor got attacked, they're like the host system got attacked. The host system has the hypervisor, and if you look really close, you'll see you've got root access with some of these vulnerabilities. You've got the Flask remote buffer overflow on Zen. So NSA took the time to write a security module for Zen, and it had a buffer overflow in it. It was remote code execution. You had this is not a good day for anybody, I think. There was through Server Core, no fault of their own, but they had a Server Core as the Hyper-V system technology. You had a remote RPC buffer overflow in it. So if you forgot to lock off the management interface for your Hyper-V installation, you just got owned over an RPC attack, and therefore your hypervisor altogether. It's a bad day for everybody. And then there's a new one. We haven't on the virtual 8088 mode. You can actually, if you're a guest in the cloud system, you can flip the CPU.
So I tried covering this a little bit before, where they essentially dropped into real mode and then tried calling interrupt table entries directly and bypassing the VMM patches on the OS.
So actually using the chip itself, the mode that the x86 processor is in, the virtualized chip, and attacking the host system.
Well, interestingly, if anybody's written a fuzzer for things like the VMware backdoor and things like that, try again in real mode.
Right. Yeah.
Some of these messages actually can't be executed from anywhere else but real mode, and different things actually happen based on where you've actually done these things. So either in real mode or actually from kernel space, interesting things happen.
So we got some really heavily technical attacks at a very low level. One of the interesting things here is Q35 attack. So you've got the no DMA feature. This actually required a binary patch to the motherboard to fix the Q35 bug. It basically, the BIOS wasn't written in a way that actually extended the feature set on the Q35 to do DMA blocking. And so if you had a huge cloud deployment and you're like, okay, well, we've got no DMA turned on, excellent for us. You find out later that the BIOS calls weren't set up right to block the DMA calls. So then you're looking at a data center going, we have to do what, patch motherboards? And that would be correct. The answer would be yes. So that's that'd be a lot of work, I guess.
I think we're starting to get close on time.
Yeah. So we'll keep going here. Did you talk about the IO? We wrote a fuzzer for the backdoor feature in VMware. So if anybody wants to download that, it's on our website. You can play with it. This basically this privileged I/O call.
Again, I highly recommend real mode.
Yeah, you can grep through some of the VMware stuff. And you can see there's a ton of features exposed in the backdoor system that VMware has. So here's great. So perfect. We're in a world, again, where we've got a lot very complex technology. How do we go about securing it? You know, a lot of doomsday type of rubbish, but there are, you know, definitely good things that are happening. Intel's made the investment, AMD's made the investment, so the idea would be make sure you do your research into your hardware selection. I mean, it really is. Like, make sure you get